Hello everyone. First of all, I want to say thank you for the invitation from the organizer. And we are from University of Science, National University, Ho Chi Minh City. I am Lê Phúc Lữ from DAC lab, Decentralized Applied Crypto lab. And today, I want to present some of our work being done for years. The decentralized storage based on erasure combinatorial batch. Yes, this is the one. This is the topic of the presentation now. Okay, so first of all, I want to talk about decentralized and centralized storage, and then I want to introduce about CBC and ECBC problem. And some of mathematical tool that we try to solve this problem and apply in decentralized. And then we have two pilot system, IoT data storing and file storing for CBC and ECBC. And so sorry if I focus a lot in theory with a lot of mathematical formula, because for easy to understand the constant, I want to give some mathematical formula. So first of all, about centralized and decentralized storage. We know that data are very important in all of aspect of life today, and data have a property of individual and business. Data can be stored on the centralized storage, and we know that the risk of centralized storage is that if the system has only one point, and therefore if that point have some issues, so we cannot access the file anymore. The system will be crashed. So decentralized should be the solution. The network node system in which each node is responsible for storing speeches of data. The nodes will work together. They will work together. And for decentralized storage, we know that it have two main properties. The first of all, we have the security aspect. Data is distributed and stored in many nodes on the network. So this satisfies the first layer is the security, right? And data is divided and encrypted, so there is an extra layer of security of the data. And about availability and efficient, user consume data from multiple nodes and richly reducing congestion of the system. And I want to talk about a solution for the decentralized storage. This is the CBC-based storage. CBC-based storage. Okay, so about the storage problem, we have N item, and M server. And each of item stored in some server. The best cost is arrangement. The best code is arrangement. Best code is arrangement for storing item on the server, so that if we want to take case file among n file, k file a subset of n file, we can retrieve on of d file by reading atmos t item from every server, from each server. And the word CBC stands for combinatorial base calls. Combinatorial base calls is proposed by the Petersons many years ago, and it's a purely combinatorial version of the base calls. Okay, so here's the figure of the storage. You can see we have some item 1, 2, 3, n. It can be considered as the files, and we have m server, and we will store each item in one or a lot of server. So the CBC problem, we consider informally that each file can store the copy of we will store a copy of n data item, and this is the optimization problem. That's we try to find a way to store. So that's the n, the number n, which is the total storage. The number of storage is as many possible. It's minimal for the given value n, m, k, and t. N, m, k, and t. And the main tool to solve this problem is a mathematical tool. We use the theorem in computer science, Horn theorem. And we reckon that the machine from the graph with two parts, x and y, we have the perfect machine from x and y. So the perfect machines is the set of h that connects every vertex of the set S to a unique vertex of y. And the theorem said that for each subset A of S, if we denote VA is the set of vertex in Y, that's connect to some vertex in the subset S. So there's the matching from S to Y, if and only if the size of VA, greater than or equal to the size of A. The size of A. Here's. This also calls the Horn marriage theorem. Like some boys has a feeling to some girl, and we can consider here phi is the boy, and the server here is the girls. So we have some relation with this theorem with our problem. Here you can see we have an example for this. We have 5 items, 1, 2, 3, and 4 to 5, and we have 3 servers. So we consider the value k equal to 2 and t equal to 1. So what's the k? K it means we want to access to any 2 items among 5 items. So the condition here is that we just allow to access as much one file in the server here. So you can see we have 5 items. We have the storage like this. So if we if we want to check the file 1 and file 2, file number 1 and file number 2, so we can take from file number 1 from the first server and file number 2 from the second server. This satisfies the condition that every server we just access at most one time, t equal to 1. For example, if we take file 2 and 3, so we can access the first and the second also. If we take file 4 and 5, so we consider the second and the third server. So this storage satisfies the given condition of the CBC problem. Okay, so if we have an issue, what happens if the server file is inactive? So we cannot access the server 3, the third server anymore. So the item file in the third server cannot be accessed anymore. So in this problem, we have another problem like ECBC. We will try to solve this situation. Like if we have the situation that some observer, some like Asmod R server among M server can be inactive at the time. So we try to store the file. We store the file suitable, also satisfy the given condition. Okay, so ECBC stands for erasure combinatorial batch code. It's the family of codes for the distributed storage system. And this not only solves the condition of CBC problem, also consider about the issue. So that some of server can be inactive in some time. And ECBC allow us recover any batch of K item, in the situation that we have R inactive node by reading Asmod T item from the remaining active node. And until 2020, this problem, this optimization problem, just solve this problem for t equal to 1. So this is the special case of the problem. Okay, so we recall the definition of the parameter here. We have 5 parameters in the total, and in the number of items, the number of server. M is the number of server, and K is number of the item. That's we try to retrieve each time, and T is the maximum number of items that's allowed to reach from each server. And also the parameter R, that's the maximum number of the inactive server. Okay, so from the given condition, we can see that we must have K less than or equal to N, right? Because K file is the subset of N files, and R less than or equal to M. And because we can have the situation that our server can be inactive, so one file has to be stored in at least plus one server. For example, if we have R equal to 5, so R equal to 7, like for example. So every file has to store in at least A server. And we can prove that M minus R has to be greater than or equal to the ceiling of K over T. This is the condition. And when the number of server is very big, it's more than the number of file. So the problem will be trivial. The problem will be trivial, and we will not consider this case, because in the real world, the number of files may be very big and the number of servers smaller. And for the application of the Horn theorem, we have some related works. In case t equal to 1 and r equal to 0, this is the original problem. It means we don't have any server can be inactive. Every server works properly. And for t equal to 1 and r greater than 0, so we have the changing of condition. That's each subset of the size k prime of k file, original k files. So the union of the sets that contain those files have the size at least k prime. By directly apply the Horn theorem. And we have some related results here. And for t greater than 1 and r greater than 0, as the base of our knowledge, this is the new result. That's we consider t not just only equal to 1. T can be any number, and r also greater than 0. It means we have the erasure aspect of the system. And by apply this proposed theorem, we can build some storage model. Satisfy the optimization problem. And here I will present one of a lot of case for this model. That's m equal to this number. And the number of files is very big. The number of files is greater than or equal to tm. So we can prove that. The optimization problem here, we have the minimal storage is this number, tm times r plus 1 plus m times n minus tm. Okay, so maybe this is hard to follow, so I will show the example for this storage. Here. We have here 17 items and our server. And we can assume that we have at some time we have equal to 2. It means 2 servers can be inactive in one time. Okay, so we can store a file in the server. And this picture, file 1, 2, 3, we store in the first server, and file 3, 4, 5. 3, 4, 5. The second, and 1, 2, 3. 1, 2, 3, and 14, 15, the first server. 3, 4, 5, 6. 1, 2, 3, 4, 5 in the second server. In this case, we have if if we have the situation that's two server here inactive, so we can check K file in the remaining server, in this example, we have K equal to, it's the same with, sorry. Oh, no. Oh, sorry. How can I? It's okay. It's okay. This is original situation that we don't have any server inactive, and K equal to 2 and T equal to 1. So we can have the storage like this. And if we have two server here can be inactive, so we have another storage like this. So we have some related problem for this one. We can consider some action, some change in on the storage model, satisfy when we have M and K or and T increasing or decreasing. So we have some way to modify the storage model, and we can have the situation that's some stable server that's never inactive. So we can store a lot of file in that server. And if the storage model is given, we can use some algorithm about the matching perfect matching to check the needed file in the server if we are given the storage model. And the last, if the file are stored in some linearly order, we can consider the aspect of the consecutive file, because maybe in the real world, some file have the related property, so they can be stored in the database in the consecutive file. So maybe we can consider this aspect. And for this aspect, for this situation, we can prove that we can solve the problem completely. We can solve the problem completely in the special case. In the special case. And the last, I have two application. I will present two application of ECBC problem. The first one here we have. We can try to apply ECBC to the real-time storage of IoT device. So this can be deployed to the domains of healthcare, agriculture, smart building, and especially we have an IoT device, and M server, which we have ASMOT R server that can be inactive at the same time. So here we have IoT device. We can consider it's the same as the files and M server. So we have the situation that maybe we have N file can be stored in M department in the building. So we can handle the situation that's maybe during the time a server can be inactive and the data cannot be stored anymore. So we need to solve some tasks. The first one, we have to store each item in at least R+1 server. And for the situation that edge server inactive, so data cannot store on this server anymore. So we have to store in another server. And when edge server reactive, so maybe we try to update the data because we know that the IoT system, the data updates in time. So we will try to update the new data that's not been stored in the time. So it can be taken from another server. Here we can see the storage model. We have like 4 storage nodes, and with the app, the mobile app and the web app, and we have the IoT blockchain. So in this situation, we also consider if some of storage model here inactive, so we also take the information, take the data from the remaining system. Okay, the next one I will introduce about the bit file storing. So we consider the storing, the file storing problem. We assume that the as much K records will be accessed from the file. And the system also similar to the original definition, we have M storage node. And we also have as much R, so storage nodes can be inactive at the same time. In this situation, we can consider as in the university, like the medicine university, we have a lot of thesis, the loss of a file of the student, and we have to distribute the file to the corresponding professor, corresponding faculty. And because we know that the medical data is very sensitive and valuable, so we have to try to find the good way to store the files of the student. And here we have the same solution. We also use ECBC solution, and the value of n can be computed. The value of n can be computed based on the given k and m. So certify that the redundant of the resources. It means the number of storage is few as possible. Here is the approach. We have the storage, the algorithm to store the file to the server. So we can hash the index of file, and we will store to the server. We store to the server, and we can apply some algorithm like binary search tree to make the inserts and updates more convenient. And here you can see the system model. We have in the university, we have like faculty 1, 2, 3, and the storage with the thesis, the data of the student, and also if we have the medicine university, so we have the data of the customer, and storage model have to be certified privacy reserving. And for example, if we apply this storage model in the university, so the student can make the thesis session by session, chapter by chapter, and they upload to the system, and just the professor corresponding to the student can access to this file. And here's some interface of the system. That's what we build from apply the ECBC problem. So we have two application of ECBC, and we will have another application. We hope in the future we can use ECBC for another application in the real world. And if you have some question about this topic, you can take this contest of me and another teacher in our university.
Thank you very much.
Okay, thank you for your listening.